is going to talk us about fractal heat diffusion in the nanoscale and subdiffraction limit in thermal imaging.
Good morning. It's a pleasure to be here. The topic of the talk is something about thermal diffusion and something about how to measure the temperature. Let me give you an outline. I always like to start with a little of the history and what was Fourier and Carnot's perspective of heat. Even though today we have much more computational power, there is some inherent ways the way heat behaves that we could learn from the early work on that. Then I specifically talk about one method to measure temperature at the smallest scale, which is based on thermoreflectance. And then I will go into the theory part of the talk. What do I mean by superdiffusion, when it happens, why it would be important, and some of the observations we had on the hydrodynamic flow of heat, and Javier Alvarez talked about it on Monday. But maybe I should first introduce where I'm coming from. Burk Center is an interdisciplinary center at Purdue that started in 2006. So it's about 11 years old. It's a large clean room, is about 2,500 square meter of clean room, a lot of micro-nano fabrication. But what is very unique is we have about 45 research groups and 200 graduate students that use the facility, and they have their offices and their labs there. And they're all sharing the labs. Labs are not owned by professors. And we have faculty from engineering, sciences, biology, health, even agriculture and pharmacy. Some of the research topics of these 45 research groups range from nano and quantum photonics, plasmonics. Vlad Shalaevs and colleagues have been leading these efforts at Burke. Purdue is home to computational nanotechnology center NanoHub. I will say you a little bit about that. That's a good resource that is available worldwide, and there is opportunity for people from everywhere to contribute and share their latest simulations as well as presentations. We have a big effort in the area of nanoelectronics, transistors, spintronics. A lot of the expertise come from the computational side, modeling of those, but also how to make some of these latest transistors. Some of the other areas, bio-nano, microelectromechanical system, energy, quite a bit of work in the area of solar cells. And two new initiatives we have. One has to do related to sensors with applications to what is called the Internet of Things, how we could introduce information technology in areas that have not penetrated, such as in agriculture, such as in food, pharmacy, and something about science of aging. You know, when professors get old, they like to do studies on how aging happens. What are these resources on NanoHub? A couple of years ago, we developed this online course, Thermoelectricity from Atoms to System, together with Professor Data and Landstrom. And the format of this NanoHub are lectures that are about 15 minutes each, 5 or 7 lectures per week, and then the total week is 5 weeks. So it's a lot of material you can cover in this. You have access to lecture notes as well as the full video synchronized, and there is a lot of simulations. That's one of the areas that we think the technology has not, MOOCs have not been used to the fullest extent. If you just put a lecture where people look at the lecture passively, like you are doing it like now, the end result of information on how much you learn is limited. You need to be active, you need to be thinking, and one way to do that is by adding online simulations. And whoever professors who come and visit us, these seminars are all recorded. And what is unique about this is, again, you can go and find online a lot of seminars, and it's 45 minutes. The question is, the topic you're interested may be in certain only 5 minutes in the middle of it. Here you have view graph and the video synchronized with the view graph, so you can quickly go there, and I'm interested to learn something about fluctuation dissipation theorem. And here in view graph 37, he talked about it. You can go back and forth and look at the video for that. And you can even look at it on the podcast on your phone these days. Let me start with the historical background part of it. What we know today as Fourier Law was developed by Fourier in 1800s, and is called Analytical Theory of Heat. And in this book, this is kind of summary of the articles he had in the last 10, 15 years. He basically had two laws that even today we use it, and the surprising part is how well these laws work. The first one is that heat flux is proportional to the temperature gradient, and the proportionality is a material property. And the second one is the first derivative of temperature with time is proportional to the second derivative of temperature with space, and the coefficient thermoconductivity divided by heat capacity, that's diffusivity. What is interesting is, how many of you know what was Fourier's reason to propose this equation, what he wanted to calculate? Anybody remembers? He wanted to calculate how long does it take for Earth to cool down. And he actually calculated, it took thousands of years, and he used these equations. And what is surprising is, what is the length scale of that comparing to what we do, and still the same equation is valid. The second part of it is that he didn't really derive this equation. He was such a mathematical genius that he said, Sir Isaac Newton has discovered the laws of how planets move. I want to see what is the laws of how the fluid that carries heat moves. At the time, people did not know that temperature is related to random motion. All the Boltzmann, all of the things, the statistical mechanics came long after, 100 years, 70, 80 years later. They thought if you have a hot object, there is a fluid in it, that is what they call the heat fluid thermos. And when you put it in contact with the cold object, that fluid moves. So he wanted to find an equation of motion for that fluid. But they knew that the equation of motion cannot be like planet, because they knew heat always go from hot to the cold, not from the cold to the hot. So they wanted to have an equation of motion that is not reversible. And with genius is that he said this type of differential equations should have that type of behavior. This is 500-page books. The first 2 chapters is how this comes. The rest of it, how do you solve it in different geometries? They didn't have computers. To solve it in different geometries, by the way, he invented Fourier series. So everything we do with the phonons and so on, for him, was a way to solve a differential equation. What is even more interesting is the analogy we do with electricity. Ohm, around the same time, proposed the same equations for current and electrical field. And Ohm himself said that I took the intuition from Fourier's work. And this is, again, has been used a lot. But what is interesting is that when you go to nanoscale devices, you never talk about Ohm's law anymore. But Fourier has been the most resilient equation. And part of the discussion today is, why is that the case? Some of the titles are cut here, but one of the things that I want to point out, there is a lot of analogy between heat and electricity. But every representation has a limitation, and the limitation is something you have to be careful. Here is an example of a state-of-the-art electronic device of nanoscale, quantum point contact. You have a sea of two-dimensional electrons that are connected by a narrow constriction. You apply a voltage between these two contacts, current flows, but then people have discovered in the last 50 years or so that conductance is quantized. There's a lot of interesting things that happen. But what I want to emphasize is that when you analyze this device, you don't worry about the contacts, you don't worry about the wires. Why is the case? Because electrical conductivity of metals that you use for these wires is 20 to 25 orders of magnitude more than electrical conductivity of insulator that confine the current, and electrical conductivity of semiconductors you're measuring. So in some sense, you have two reservoirs of voltage next to each other, and you can really analyze behavior of a system, quantum system, nanosystem, without worrying what happens with the boundaries. How do we look at nano-object? You have seen a lot of papers about, for example, what is the thermal conductivity of a carbon nanotube. But really, how would we measure that? Well, we have a thermometer. We need to connect this to the nano-object. And if we want to measure the temperature on this side, the thermal contact from here to the thermometer should be much lower than the thermal contact with other object, because if not, I measure the temperature of other object. Fundamental difference between heat and electricity is the biggest ratio between high and low electrical conductivity material is a factor of 100,000. It's not 20 orders of magnitude. And as a result, this idea that you can measure the temperature precisely without worrying about how the thermometer is connected, you have to be careful. And even harder is the notion of the heat conduction. Again, in a molecular dynamics or any type of model, you always put a reservoir. And then you calculate heat flux and so on. There is no such a thing as a nanoscale reservoir. For electricity, again, you can do that because the large differences between electrical conductivity of metals and insulators, you can really bring the voltage probe to the two sides of the nanoscale device. We can mimic that, and that's what people, a few very nice experimental work is that they put this in a suspended platform, and they take a lot of care, typically, PhD students, 6 months of work, to make sure that the heat only comes here, you measure temperature precisely. You define a thermal conductivity. But from a practical point of view, that's never useful because, whenever I have any electronic device, what I have is a heat source, and I have the heat sink, which is the lab. And the thermal resistances are not negligible. So boundary conditions matter in real devices. Let me show you a real device. So what we mean when we study a device, this is a high electromobility device. There is a source and drain and a gate. The gate controls how the current goes from source and drain. The reason there's two of them, you just want to get more current. These are the type of devices used for power electronics. What is the cross section? If I cut it here in the middle, this is really what happens in the device. I have a substrate. These are thicknesses in micron. In the top microns, I put some materials, and then there is a source and a drain and a gate. Typically, the gate, quarter of a micron, very small. That's where the nano comes in. And I control the current from source to the drain by changing the gate voltage. What happens is that the transport there is some dissipation. It heats up, and that heating is what we need to minimize, and that's what makes the device perform less well. Two effects about heating are important. Typically, heating increases the electron resistance, decreases the mobility, so the device becomes less efficient. That's one thing. The second is reliability. A lot of the devices have a finite lifetime, and the lifetime is exponentially related to temperature. Typically, 10 degrees excess in temperature reduces the lifetime by a factor of 2. So really, we need to consider the temperature at the location of the heat and we need to minimize it. So what is the realistic boundary condition? I have a material with micro and nanoscale layers. I have a heat source, and I have a heat sink far away. There is no two reservoirs. How would you measure temperature of a device? The picture I showed you is an optical picture. You see by your eye that these are metals, and these are semiconductors a little darker. Reflection coefficient on every material is a function of temperature. So you can use what you see by your eye as a thermometer. But the effect is small. For every 1 degree temperature change, the reflection coefficient changes 1 part in 10,000 to 1 part in 100,000. So if this device is off, all of it will be the same temperature. If the device is on, for example, the metal here could be 30 degrees hotter than here. 30 degrees means 30 times 10 minus 4 change in reflection. Can your eye see such a small change? No. Can any camera see such a small change? No. But how do we measure small signals? The way we measure small signals, the way your cell phone works, is always the method of lock-in detection, is that you change your signal by a known frequency. Noise is broadband. If you do narrow filtering, you can measure signal over noise with 1 part in millions. So the idea is that I have a LED, I shine the device, but the device, I have a very precise timing between the pulses that apply to the device and the pulses of light that take pictures of this device at a specific delay after the electrical pulse. So here is the electrical excitation. Here is the temperature of the device, heats up, cool down, heats up, cool down. And with this pulse of light, I can measure reflection at this point. And if I do it precisely, I can measure temperature to below 0.1 degrees. Is a visible wavelength, I can go down to hundreds of nanometer spatial resolution, and with LEDs or lasers, I can do this stroboscopic way of measurement down to sub-nanoseconds. So I can really measure temperature very fast at the smallest scale. This is the first paper we work on this. This is another review article more recently. Now this is commercialized. We have a company, Microsange, that commercializes the system, and we have something like about 30, 40 of these around the world. This is probably the most accurate way of measuring temperature of electronic devices, but don't take my word for it, because we started the company, so there is a conflict of interest in explaining what will be the best measurement technique. But these are the results you obtain. So here is a gallium nitride device. You can see the shadows of the source, drain, and the gate. For 10 microseconds, the device is on, and then the device is off. Here's a temperature at 3 locations, the channel, the gate, and the drain. Let me just go back and show you in this picture. We are measuring the temperature at this location, and this location. These are within a few microns or even sub-microns. One of the things you realize, temperatures change in the time scale of a few microseconds, but it's very heterogeneous. A channel, 120-degree heating, while the drain, which is only a few microns away, is only 40 degrees. There is a huge temperature gradient inside the device. And this is a major reliability issue, and that's one of the reasons people need to characterize this. For people who are interested in more interesting kind of nanophysics, using this technique, you can even see what happens inside the device. Vanadium oxide is a material that goes from metal to insulator under stress conditions. Here is a beam of vanadium oxide, diameter less than a micron, the length is 7 micron or so. And optical image, you see some regions that are dark, some regions are a little brighter. From experience, people know that the dark regions and the bright regions are insulator metal. So I have a nanowire where there is lots of regions of metals and semiconductors inside of it. And I can send current through this. The question is, how do I know these exist? If I only measure the resistance from one end to the other, I have an average number. You don't know the domains. Here are the thermal images of the same device for Peltier and the Joule. And very quickly, when a current flows inside the device, the current causes dissipation. and this dissipation, which is Joule effect, locally hit the device. That's what happened in a resistor. Joule effect is fully irreversible. What it means is that if the current goes from right to the left or left to the right, you should measure the same amount of heating. So heating is proportional to the current square, resistance time current square. I can separate that if the current is modulated at frequency omega, and I look at 2 omega, I only measure Joule heating. But at the interface, when electrons go from metal to semiconductor, there is a change in average energy of electron gas. That's a Peltier cooling or Peltier heating. That's irreversible heat exchange. And that way, you can see some temperature changes. What is interesting is that I have a thermal image. I look at 1 omega component. I tell me what happens from a reversible point of view. I look at the 2 omega component. I tell me what happens from an irreversible point of view. You look at it, you say, well, this looks the same. How do you know you measured it right? You know, as an experimentalist, whenever you have any data, the first thing is that what went wrong during the experiment? Is it because there is some mixing, some of the way it didn't work? But the advantage of the sinusoidal simulations is you can look at the phase. The phase tells you much more than the amplitude. And here you see a distinct differences. What the phase here tells us, Joule heating happens in the wire. The heat should go somewhere. The only place it can go is in the substrate. But here, you have Peltier cooling, Peltier heating, Peltier cooling. They're close each other. They actually heat and cool each other. The heat doesn't go to the substrate. So from this, you already know that the two types of heats are very different. Again, if you do the end-to-end measurements, the resistance versus temperature of these beams, you see that they go from high resistance to low resistance in a small temperature range. So you know it's a phase change material. You go from a metal to insulator over a wide temperature range. So here you have all domains that are resistive. Here you have all domains that are metallic. And in between, you have multi-domains, and that's how we can see what happens inside the device. Let me tell you a few words about how can we increase the resolution of this temperature. This is already good. You can see things on the order of 200 nanometer, which is the diffraction limit of light. What does diffraction limit means? On a substrate, we can fabricate a heater. What is a heater? It's a metal line with 2 probes. With these 2, you send current, and the current heats up here. With these 2 tiny probes, you measure the voltage, so you measure the resistance of these as a thermometer. So I have an indication of the average temperature of this line. If this line is 1 micron, is an optical image, you can see it. If it's half a micron, you can barely see it. If it's 0.2 micron, you don't see it. Why do you get this? Is what is called the diffraction function. A point source, because of the finite numerical aperture of an imaging system, appears as a sinc function, so broadens, and this broadening, if it's too small, make you not to see the object. What happened when you measure the temperature of the device? As I said, what do you do to measure the temperature is you take this optical image, you turn on and off the device at 1 frequency, and then you lock into that frequency at each pixel of the image. It should tell you where are the hot and the cold spots. What we were surprised is that, of course, at 1 micron, you measure the temperature, you see how the current goes, how it heats up here, beautiful heating. But we can even measure the temperature out to 0.2 micron. You know, as an experimentalist, well, this is what we measure. So, but it looks like we are breaking the laws of diffraction to measure temperature, but it applies to optics. Any ideas how can you break the laws of diffraction? You know, there are certain laws in physics, is like the second law of thermodynamics, and there are certain laws of physics, laws of diffraction. The analogy I give is like speed limit in highways. You know, it's a law you shouldn't go above, but you know, some people go above and so on. Diffraction has to do with a blurring function that happened with the optical system. Why is it that we can see the signal from a tiny device, even if it's below the diffraction? It was a pure luck. What I mean by luck is not that it happened once and it doesn't happen again. What I mean is that the metals that are made here have a thermoreflectance coefficient that has a different sign as the semiconductor. So as the device heats up, so here is brighter than here, but as the device heats up, the reflection coefficient of this one goes up and the other one goes down. And whenever there is a phase change, you can go below diffraction because this is amplitude square. Before squaring it, a lot of things could happen. That's, by the way, how they make nanometer transistor using optical lithography. They use phase masks. So we have the natural one here. How the temperature distribution look like comparing to the experiment. So here is a distance in microns. The black line is ANSY's simulation of the actual heater that we should get based on the Fourier Law. So again, Fourier works quite well, up to 1 micron heater. And because of diffraction, what I call filters, the effect of diffraction, and because of the sign change, there is a zero crossing. But blue is the modeling, which has been blurred, and the red. The blue is the experiment, and they two match quite well, and the temperature on top of a device match quite well what we expected. If we do the same thing with 1/4 of a micron heater line, what we see is quite surprising. So what we see is the temperature on top of a heater line, theory and experiment match, but the near the heater line, theory and experiment have significant deviation. Basically, if I have a heating of 15 degrees here, about a 1/4 of a micron away, Fourier Law tell me it should heat up about 7 degrees. We only measure heating of 2-3 degrees. This is error bar, so definitely V is above. So we were puzzled for quite some time, and what we did is we said there was something wrong with optics. You know, if you send it for referee, you know, make sure your optical system is okay. Maybe you didn't clarify. So what we did is we fabricated next to the heater another heater very close by, and we used that as an electrical thermometer, and we got the same thing. This device next to it is cooler than what Fourier predicts. It took us some time, but I guess in Javier's work, explain what happens is when the devices are smaller than 1/2 a micron or so, you have a heat source on top of a substrate, you have vectors of a heat flux and vectors of a temperature gradient where they can be basically not parallel, and this is one of the indication of a hydrodynamic flow of heat, because if the heat is purely diffusive, the two should be always parallel. And with this type of modeling, Javier and his group were able to exactly explain what is the full temperature distribution which was here. And I guess Javier showed it on Monday, so I don't go over those. One question is, can we go below diffraction limit? And, you know, I don't want to bore you too much with optics. Let me skip this one. If you're still interested at the end, I can tell you that going below the diffraction limit is really an information point of view, information theory point of view. What I mean is that if I have an object that is heated, when it's diffracted, every point becomes blurs, and there is some noise. This is what you measure. But at every point, you have information about neighboring points. So if you know the inverse problem methodology from image deconvolution, image sharpening, is used all the time, you know, in YouTubes and so on, you can apply it to here. And we have been able with this to go to 100 nanometer spatial resolution. But I keep it a little later in case there are questions. Any questions so far? Yes. So the question is, is there a limit in the smallest length? You can measure temperature gradient, of course, yes. It depends on the signal to noise ratio. If we do directly without any signal processing, the smallest length is 250 to 300 nanometer. That's what diffraction limit gives you. If you use the inverse methodology that I described, the inverse problem is very sensitive to signal to noise. With the signal to noise that we have today, which is something on the order of 20 dB, factor of 100 for very nanoscale measurements, or factor of 1,000 in some of the very good, clear, very smooth samples, we can go down to 100 nanometer. 100 nanometer non-contact far field measurement is our kind of the best result we have shown. So let me now to go to the second part of this, or maybe this hydrodynamic effects is one of the things that happen at the smallest scale. But there is another thing that happens, which is modified Fourier that I want to go over it, that is of a different nature. First of all, I should tell you how do we measure thermal conductivity of a very tiny film. In this case, we have a 3 micron of a superlattice, silicon and silicon germanium. 3 micron is 1/10 of a human hair thick. How do you measure how much thermal conduction it had? Again, it's a bulk material, thin film material sitting on a substrate. I'm interested in thermal conduction perpendicular to the plane. Lasers allows us to do that. You put an aluminum film. Aluminum film absorbs light at 780 nanometer that comes from a Ti-sapphire laser. The laser heat up the surface at time 0. Then the heat is dissipated, only going down. There is no other place for the heat to go. So the sample reflection, which is a measure of temperature, increases at time t equals 0, and then decreases. And here our reflection versus time, here is 1,000 picosecond. It's very fast. You need femtosecond laser to measure this. And what you see, 2 samples, one of them decays faster than the other. You don't need modeling. By eye, you know that this sample should have a higher thermal conductivity than this one, correct? The higher is the thermal conductivity, the faster the heat from here goes down. About 10 years ago, when we were naive, we thought, this is the fit based on Fourier, and we get a thermal conductivity, beautiful, 2.8, and if you're careful, maybe we can give another digit. There are some tiny variations, but if you're an experimentalist, you know that you cannot fit everything perfectly all the time. This is a good trend. You can publish in good papers about that. So metal film is heated by the laser pulse. It acts as a heat source and a temperature sensor. Temperature decay is defined by a thermal conductivity. But as we fit things with thermal conductivity, we forget some of the physical limitations. Before I go, there is another set of work that happened in the last 20 years or so. It's called thin film thermal conductivity. Silicon, if it's more than a micron, if you buy it from any vendor, thermal conductivity is about 130, 140. People made thin film of silicon, and they realized that when the silicon is 0.1 micron, 100 nanometer, its thermal conductivity is significantly reduced when you go to tens of nanometer, a factor of 3 or 4 reduction. Again, this modeling says Fourier Law with an added scattering because the film is thin. Makes sense, isn't it? It fits quite well, lots of data, lots of groups. There is not much question. But for some time, people have been worrying that there is something wrong about Fourier. What is wrong about Fourier? And there's a nice paper by Joseph et al. In Heat Waves in Review of Modern Physics in '89 that summarizes the understanding of the field. What is the problem with Fourier is that this is a parabolic differential equation. The speed of information transfer in a parabolic differential equation is infinite. What does it mean? I have a sample 0.1 micron of diamond. At time t equals 0, everywhere is the same temperature. I apply a pulse of heat here. temperature increases and you get this profile at early times, this is normalized time. At later times, you get the steady state and you can define thermal conductivity. But at time 1 femtosecond after the heat pulse, temperature everywhere in the field is non-zero. The information at this boundary has propagated everywhere in the sample instantaneously, and that's the characteristics of this differential equation. There's nothing else you could do. And you know Einstein would not have liked it, correct? There's something called causality. How do you introduce causality? This equation is not causal. Well, if you're a mathematician, you cure things by adding terms to the differential equation. So Cattaneo and people said, in addition to the first derivative of temperature with time, let's add a second derivative of temperature with time. Second derivative with time, second derivative with space give you a wave behavior. Wave behavior has, it's called hyperbolic differential equation, has a finite speed, and this is the temperature you calculate. At early times, temperature only gone to this distance, later time, this distance. What is interesting is original equation had only one parameter. You just added one more, but it's very physical. This parameter described diffusion. This parameter described the speed of wave propagation. Very different result. The first paper that was able to use state-of-the-art computation said these are all approximation. Let's solve Boltzmann equation. This is one of the early papers of Arun Majumdar. I think this is his only paper with his wife, Joshi, where he calculated this for diamond. Again, very realistic cases, nothing fancy. But this is the solution to the Boltzmann, the red one. First of all, Boltzmann, when you solve it with this form, obeys the right behavior. At early times, information or the temperature has only propagated finite distance. Only later goes, but the shape of the red and the blue has nothing to do with each other. So the question is, well, this something that very different people have not observed it. This, by the way, looks innocent, but when you go from partial ordinary differential equation to this partial differential equation, your amount of information is much more, and all of the physics is in a scattering term, and you lose these fundamental parameters like here. You can go back and extract the fundamental parameters, but I want to tell you something about Boltzmann that you should know. Do you know that Boltzmann committed suicide because people did not accept this equation? What was wrong with the physicists at this time? Or what was wrong with Boltzmann, but Again, it's interesting, because after 100 years we use it so much, we forget how much resistance it was to use that equation. Anybody knows? Boltzmann, poor guy, he killed himself. You should at least know why he killed himself.
Newton's law is time irreversible, and this one is time irreversible.
That's a very good point. So that's the reason is that at the time of the Boltzmann, people, well, taking Newton, since the laws of physics are there, for some things we have discovered, for something we haven't discovered, Newton's law was reversible. Even at the time, Maxwell's law was coming about, fully reversible. By adding this little thing, this becomes irreversible. And okay, there is always scattering. No, that's not, they said this is not fundamental. You should not use reversibility fundamentally. But what is even more interesting is, by writing this, we mix heat transport and energy transport. And that is an area that requires a lot of thinking. What I mean is this: I have an energy packet. What is energy? Is excess kinetic energy in one part. That excess kinetic energy can move in the sample, and it can come back. You don't violate anything. I have not done anything. And when you solve this naively, you have the energy transport, but by adding the scattering, you lose reversibility. In some cases, you can define temperature. What is the key challenge is that this is a stochastic differential equation. How you introduce stochasticity matters. This is probabilistic treatment. When you put a relaxation time approximation, you make a fundamental assumption about what is the stochasticity of this, and that changes the nature of the equation. To tell you, every representation has a limitation. I told you that this is a representation that is microscopic. It has advantages. The limitation is you lose these macroscopic numbers directly in the equation. The second is how this irreversibility. But let me go back to something that you probably have heard about it, which is Fick's law. Fick was 20-some years after Boltzmann, after Fourier, 1855. He is actually the one who provided some proof why heat equation should follow the diffusion equation. You need two equations to get to the diffusion equation. He wrote it for number particles, but if you put, instead of a number temperature, and instead of a current, heat current, this is exactly Fourier equation. Two equations are needed. One is continuity. The change in the number, or the change in temperature, is due to the divergence of a heat flux. That has to do with bin counting. Something coming in, going out. The change at a location depends how much things go out. This is what divergence means. But there is now an approximation, a linear response. Heat flux is proportional to gradient of a temperature gradient, of a gradient in temperature. And this is an assumption, and again was mentioned earlier this week, that this is a nonsense. You don't demonstrate it, you put it there. From these two, you get the diffusion equation. What is the solution of this? Is differential equation. One way to solve this is using Green's function. The Green's function solution to this, n, is this type of exponential where you have distance square and time, and this is what also you heard. If I start with the perturbation here, at time t equals 0, as time goes on, perturbation propagates, and the mean square displacement is going with time. That's what we understand as diffusion. If I have a perfume here,